to another edition of Calculus Long Distance Learning Style. Today I decided to take it al fresco, so we're calling it Patio Productions. And so I'm here straight from my backyard, just, I had to get out of the house. I'm just saying. What we're going to do is we're going to do the last official notes page from your packet. Let's just get started. So let me get my screen shared and this PowerPoint pulled up. And we're just going to get right started here, guys. So what we're doing is we're talking about now doing finally some calculus with our polar, which is like super duper duper exciting. And guys, I'm not even kidding. It's going to be pretty amazing. We are now going to actually find slopes, equations of lines, and even like area. Oh, it's going to be so exciting. Like I can't even, like, it's just going to be like so amazing, you guys, so amazing. So let's go ahead and get started. You are going to need to do slope of a polar curve, okay? So we're going to write this down in the box that is definitely on our note packet right there, and it's going to look familiar, okay? It's going to look very parametric style, and that is exactly what it is, okay? This parametric style says if I want dy dx, we know that when we're in polar, we always have our r equals, and then it's something in terms of theta. So theta is now going to be our parameter, okay? We're going to take the dy d theta and put it over the dx d theta. Very nice, okay? So basically, the key to this is taking your polar equation, turning it into parametric, and then taking the derivative, okay? And then, of course, your derivative is your slope, okay? Oh, I forgot to call it out. Here I go. Derivative. I knew you guys did it. I knew you did. I knew you did. You totally said slope. I knew it. Okay, so let's go ahead and just jam right into example number 5. Honestly, it's a pretty easy example. The only like tricky part is this. There's lots of trig functions to take. So, but like whatever, we can do that. Okay, so this says find the slope of the curve at the point where theta is pi over 6, and then use it to find the equation of the tangent line. Okay, so we know that when we find the equation of a tangent line, folks, we need a point and a slope. So let's go ahead and get that slope first, and then we'll go and figure out what the coordinate is for the point, okay? So, and again, if we're going to write the equation of a tangent line, we're writing this in Cartesian, right? So we need everything to switch into terms of x's and y's. Not a problem. It just takes a minute, okay? So the first thing what we're going to do is we're going to change each of we're going to get to parametric. So in getting to parametric, we're going to, from yesterday's note, so if you go backwards in your note packet, you will see that what we wrote down yesterday is to how, if you want to change a polar graph and do it parametrically, it's going to be x equals r cosine theta. Okay, so the cosine of theta is there. I'm trying to find my little marker guy. Okay, and so the cosine of theta is there, but what do we do for the r? Folks, we're going to plug in what the function is. This is right here our r value. So it's f of theta times cosine theta. And that is, in fact, our f of theta. So we're going to make this be 2 times sine of 3 theta, which is just straight, right? Literally, guys, I just grabbed it from the question. And then times cosine theta. That's the x component. And then we're going to do the same thing for the y guy. We're going to have r sine of theta. So f of theta, sine of theta. And we just plop the function in again. So 2 sine of 3 theta, and then times sine of theta. Now, these are now our parametric equations for x and y. And we know that if we're going to find the equation of a tangent line, we need the slope and the point. So let's go get the slope, okay? We're going to say that dy dx, because we need it in terms of y and x, of course, is going to need to be dy d theta over dx d theta. So the dy d theta. Okay, very common mistake, guys. Do not make this mistake. It's putting the x guy on top of the y guy. In fact, I want to be honest with you. I was prepping for this lesson. I made that mistake. Hello, dummy. It's because I did not think to myself, oh, the y guy needs to go on the top. So just be careful. I speak from experience. Okay, and so what we're going to do is we're going to look at the y guy first. And guys, this is actually 2 functions put together, which means we're going to need the product rule. Not a problem. We could totally do it, but we're for sure going to need the product rule. And then actually when we do this guy right here, we're going to need the chain rule too. It just looks like a really long guy, but it's actually totally fine. Okay, so product rule, remember, you're supposed to take the first times the derivative of the second. So the first is 2 sine of 3 theta times the derivative of the second, which would be derivative of sine is cosine. And I'm going to add the second times the derivative of the first. Okay, the derivative, so here's the second, the sine of theta. The derivative of this guy, technically the function is a sine function. So sine's derivative is cosine. We left the inside alone, but then I had to multiply by the inside function, right? That guy's derivative of a 3. And so this 3 got multiplied by the 2, and that's why I have a 6 out front. We're going to do the same thing now for the x guys, okay? We're going to do the product rule. So just, I'm going to reiterate it, okay? Just, of course. We're going to do the first times the derivative of the second, so it's 2 sine of 3 theta, and then times negative sine of theta, and I floated my negative out front. Then I'm going to add the, so we did first times derivative of second plus second times derivative of the first. And so we have our cosine theta, and then the derivative of the first we already did up top. So it is 6 cosine of 3 theta. Now, darlings, all we have to do now is evaluate this, okay, at pi over 6. So it's just a matter of plugging in the numbers, okay? So you're going to have a 2. So we're plugging in pi over 6 every single time that we have our theta, like theta here and theta here and theta here, all the places where we have theta. So on this one, 3 times pi over 6 is actually a pi over 2. So we got a 2 times sine of pi over 2, which is a 1. And then cosine of pi over 6. So cosine of pi over 6 is going to be a rad 3 over, nope, pi over 6. If you could see my arm, I don't know if you guys can see me or not, but I did the wrong angle. Cosine of pi over 6 is a rad 3 over 2. And then we're going to go 6 times cosine of pi over 2 is actually 0. And then sine of pi over 6 is a 1/2. And then we'll do the same thing on the bottom. 2 times 1, and then sine of pi over 6 is 1/2. And then we got 6 times 0 times cosine of pi over 6 is a rad 3 over 2. Guys, what's super nice, this one cleans up super nice. And what we get is the guys that have the 0 in them totally go away. We can cancel stuff on the top. The 2's cancel, these 2's cancel, and literally all we're left with is a negative 1/3. So lovely. That is my slope. Woo-hoo! I'm halfway done with the question. Now I need to find the coordinate, okay? So the x and y guys are still on the top. Let me find my coordinate. For my equation of the tangent line, I need a point and a slope. So let's see what the point is. I'm just going to go back to the originals, guys. Like here's the x value and here's the y value. So let's grab those 2 values and plug in pi over 6 and see what it turns out to be. So for the x, it's going to be 2 times sine over pi over 2 and then cosine of pi over 6, which just is a 2 times a 1 times a rad 3 over 2. Just gives me rad 3. And then for the y coordinate, I'm going to have 2 times sine of pi over 2 times sine of pi over 6. So it's 2 times 1 times 1/2, and it's 1. Guys, my coordinate is rad 3, 1. And then so easy. We write it in point slope formula. And here is the equation of my tangent line. Y minus 1 equals negative rad 3 times x minus rad 3. And that's it. Good to go. This is how you would write the equation of a tangent line and find some slope using polar. So fun. So now let's go to the next topic. So now we're going to talk about area enclosed by polar curves. So we're just going to do a little teensy bit of theory, just the teensiest bit, guys, okay? And so we want a formula that allows not for like when we first learned area under a curve, we did like strips. We're not going to do strips. We're going to now do like wedges because that's how a polar curve is traced. You start at the origin and then you're like sweeping the area of you're sweeping a curve. So we're basically going to have like little wedges of a circle. They're officially called sectors. That is their geometry name. And so this is what we would have before, right? This is how we did our Riemann sums. And then we just made our just super teensy guys. We made them go, the widths of those rectangles go to 0. So now we're just going to have the portion of a curve and we're going to make the width, I guess the angle, the theta go to 0. So officially the area for the, for a sector in, if we're doing it in radians, and we could have nabbed this from a pre-calc lesson, is area is 1/2 of r squared theta. Okay, but we want the little pieces to be shrinking up, like shrinking, shrinking, shrinking. And then what we get is that dA is going to be 1/2 of r squared and then d theta. So we're just shrinking up the guys, and we're going to have the little bitty strips of area that correlate to the little bitty, like teensy meensy, super, 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 super values of theta. Okay, so let's go ahead and write down what our formula then is going to be, because we're now going to like add all of these up. Right, so we have to do the sum of them. Okay, and so we know that summation totally turns into an integral. So let's write it down. So this is going to be the area of a region between the origin and the polar curve. I think honestly that this word of, let me find my mousy mouse. Where am I drawing? Where? I'm drawing down there. That's super not what I wanted to do. Erase, JK. Okay, so this between the origin and the polar curve, a better way to maybe think about that is having it I describe it as the area that gets swept, right? So when you do your polar curve, you can almost like think about your elbow anchoring at the origin, and then the polar curve is sweeping through the quadrants. So this is like the area that is swept, okay? So we're going to have our theta, our start theta right here at alpha, our end theta right here at beta, and then r is going to be some function of theta, okay? So we're going to have just the area of the sectors added all up. So it's going to be the integral from alpha to beta, and then it's 1/2 of the r squared d theta. Okay, what you can do is you can factor out, not really factor, but push out the 1/2, and then really remember r is just a function of theta. So whatever the function is, you just square that whole function. I will let you know right now that sometimes we do these by hand, and sometimes we just do them on the graphing calculator. I think in our notes today, we're going to do one of them by hand, and then the other ones we're just going to do by graphing calculator. Okay, so this says find the area of the region enclosed by the cardioid. R equals 2 parentheses 1 plus cosine theta. I know it's a cardioid if I go ahead and distribute that 2. And so we talked about this a couple of days ago, that means it's a nice steady heartbeat. Most of the guy is graphed over there on the cosine, and this is what it would look like. If you were nervous, you could have put it in your graphing calculator, as long as you're in polar mode, and then you're golden, and radians, of course. Okay, so we're going to think to ourselves, how can I find all of this area? Okay, so if I think about it, when I start graphing, I'm starting at theta equals 0, and then all of this is swept, right? It's swept this way, it comes back in, it goes to 0, and then it's swept this way, all like this, and then poof, we get right back to where we started. So we're going to find that area right there. So I'm going to take my limits of integration to go from 0 to 2 pi, and then I slide the 1/2 out in the front, and then this right here is just the function. Okay, the function is 2 plus 2 cosine theta quantity squared. Now, it would be very easy to toss this in a calculator, and so you could, but this is the one example that I am going to do by hand. It does use an identity, but if I were to ask you to do it by hand, I would like give you that information like 100% for sure. So let's just go ahead and do this by hand, not a big deal. We're going to have 1/2 is the integral from 0 to 2 pi. I expanded this by squaring it. I get a 4 plus an 8 cosine theta, and then plus a 4 cosine squared theta. And I could take the antiderivative of a 4. I can take the antiderivative of an 8 cosine theta. I can't take the antiderivative of this. There is a lovely cutesy identity that we're going to use, that cosine squared theta is 1 plus cosine of 2 theta over 2. And that is, in fact, what I'm going to plug in for the cosine squared spot. The 1/2 gets to cancel, and so I end up getting a 2. Oh, just kidding. I factored out a 2 out of the whole thing. Okay, I was like, what in the world just happened? Okay, you don't have to do this, but that's what I decided to do. I took this guy right here, and I factored out a 2 out of the whole thing, and you can see that in the front. Can you guys see right here that there's no 1/2 anymore because I doubled the whole thing, so I took something out, and then I also replaced it with the identity. So this cosine squared right here, this cosine squared theta has now become 1 plus cosine of 2 theta, and then all over 2. These 2's are now going to cancel, which is super nice. This guy right here and this guy right here. We're going to combine some like terms. It's going to be amazing. And we get just a 3 plus 4 cosine theta, and then cosine of 2 theta d theta. Finding these antiderivatives are pretty easy. This would be a 3 theta Antiderivative of the 4 cosine theta is a 4 sine theta. And then the antiderivative here, thinking about counteracting a chain rule, would be a sine of 2 theta and then a 1/2. We are going to evaluate this baby from 0 to 2 pi. And let's just plop the numbers in. So if I plop in the 2 pi first, of course, that's what we do first, we get a 6 pi, and then sine of 2 pi and sine of 4 pi are both 0. I plug in 0, and then bloop, everything turns out to be 0. So even though there was an identity in there, it actually turns out super cute, and the answer is just a 6 pi. There it is. The end. So let's go ahead and turn the page on our notes to the last page, and we're going to do 2 more examples. Okay, so one of the examples here, it just says find the area inside, not the entire curve, but just the smaller loop of the limicon. Oh, this is going to be cool. Man, this is nice. Okay, so the first thing would be to graph our limicon. Either you do it in your head or, well, of course you draw it on paper. What am I thinking? What am I thinking? Of course, we're going to draw it. But you could draw it from your calculator or just from your brain, but you put it on a piece of paper. There it is. And we're going to figure out what's just inside the inner loop. Okay, just that part right there. So I'm kind of thinking that I need to figure out where the values of R are 0. Okay, so I'm going to erase this. But basically what would happen, guys, if I started by plugging in 0 for cosine, it would start right here. This is like the spot that it would start, and then it would start tracing it. So we have values that are tracing, they're tracing. Probably right here, guys, is a value where cosine is, not cosine, excuse me, where the theta is a pi over 2, right? Because if you think about it, cosine of pi over 2 would be 0, and then this value would be 1. And then look, guys, it's just going to sweep. So we need to figure out, ding, right here, where the R value is 0. Then it sweeps around and goes back to an R value of 0, and then the R's are just doing what they do. So let me erase this so that it's not in the way of our picture. And it says, where are the R values 0? So let's just set the equation equal to 0. So we're going to say 0 equals 1 plus 2 cosine theta, which means that move the 1, make it be a -1, divide by 2. And so you're thinking to yourself, where in the unit circle is cosine equal to a -1/2? Those values happen at a 2 pi over 3 and a 4 pi over 3. Folks, dun, 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 that is our limits of integration. And so those are our limits of integration. So here I go. I'm going to put my 1/2 in front. I'm going to go from a 2 pi over 3 to a 4 pi over 3. And then we'll have 1 plus 2 cosine of theta squared, d theta. If I were to do this by hand, which, you know, I'm super like, that'd be so boring if I did this by hand again. Instead, I'm just going to plop this in my calculator. So be very careful. Watch your parentheses. Make sure that you do it lovely. Do a good job. And then this is the answer, 0.0544. 0.0. That's not right. I said it wrong. Silly Mrs. Fox. It is 0.544. That is the area right there. Okay, so we did not have to do this one by hand. The other one was just as an example of showing it that you could do it by hand. Okay, one more thing, okay? Not only can we do like the area swept by one curve, but now we can do 2 curves. Oh, this is so very exciting, okay? So probably on this one, what is of most importance is figuring out which curve is, quote, the outside curve and which one's the inside curve. When we do our regular functions, just like in the Cartesian, you always do top curve minus bottom curve. So that's exactly what we're doing, but now it's going to be the most outside curve minus the inside curve when we think about doing like a radius value, okay? So basically, you're just going to take, where'd my little pencil go again? Here you are, pencil. Okay, so basically you're going to take like the outside value and then you're going to subtract the inside value, okay? And so let me erase all these things. Sorry about that. You can factor out the 1/2 and combine them to be one thing. And so it's your R2 value squared minus your R1 value squared. Folks, it just means it's not a big deal. It's the outside function minus the inside function. That's all you have to worry about, okay? So maybe write that down as outside minus inside, and then let's do one more example, and then we are done. Here we go. Okay, we're going to find the area of the region that lies inside the circle of r equals 1, but then outside the cardioid, okay? So these actually have intersection points. So I'm going to graph a circle of radius 1, which means the center is at the origin, and we just draw radius of 1. This is the cardioid because this is a 1, and then you guys, there's an invisible 1 right here. And so most of it's over here on the negative x-axis, and then here's our beautiful guy. We are actually looking for inside the red guy, but outside the blue guy. And so what that means is it's this like little moon looking shape right there. Like, so cute, right? Okay, so what we're going to think about is if I were to draw like a spike, right? Like thinking about drawing a radius, how would that work and where would it hit the curve? So I'm going to draw an example of one in right here. Okay, it's a little bit crooked. Sorry about that. But can you see that it's hitting the red curve on the outside, but then right here on the inside, it's hitting the blue curve? Okay, so that means that the circle is going to be our outside curve and our blue guy is going to be the inside curve. Okay, time out. This is not the question, but what if I had done the other side? Okay, so let me just draw an example really fast. If I had done this side, check it out. The blue guy is on the outside and the red guy is on the inside if I wanted like this area right here of this moon shape. Okay, so we're just doing just this one guy. So I'm going to draw this guy back in. And if you draw one example, red is on the outside, blue is on the inside. Okay, so the outside guy is the r equals 1. The inside guy is the 1 minus 1 cosine theta. Okay, so what I'm going to start is I'm going to start by writing the guys, and I'm going to fill in these limits of integration in just a minute. So we have a 1/2 right in the front. We have our integral. I'm going to get to those limits of integration, I promise. The outside curve is the 1, so I do 1 squared. The inside curve is the 1 minus cosine squared. That whole thing quantity squared, and I have a subtraction sign. So now I need to figure out the limits of integration. One thing that I'm thinking about doing is just finding the top half to make my life just a little bit easier, right? And doubling my answer because it is symmetric. This stuff right here is totally the same as this stuff right here. It's actually exactly the same. And so that's what I think I'm going to do. I'm going to change my limits of integration. So I'm going to make this be a 2, and then I'm going to cancel the 2 and the 1/2, and now I'm going to adjust my limits of integration. Okay, there's 2 ways to think about this. Number one, you can just think about tracing the thetas, okay? This is theta equals 0 right here, and then I'm tracing up to here to be that theta equals a pi over 2. Okay, so that's one way to think about it. Another way to think about it, because there is more than one way to do stuff, is if we're thinking about this cardioid, we want it when this guy is 0, when the radius is 0, and then up here when the radius is 1. So the cardioid, we can think about this guy having a radius of 0, and then up here, it has a radius of 1, and that's another way that I can solve for it. I'm just trying to give you like multiple tools because you never know what you're going to need, okay? So if I'm doing this one, the only place that cosine is 1/2 on our regular unit circle going from 0 to 2 pi is at 0, okay? And then I want that guy to be 1. So where can I get that cosine is 0? Cosine is 0 in 2 spots, at a pi over 2 and a 3 pi over 2. So I'm thinking we should just go with the pi over 2 guy. And so that's the first spot where it happens. And so, dun, 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 this is our beautiful integral that we're going to now take. So of course I'm going to let you do this by your graphing calculator. So you're going to enter it all in, tap, 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 and it's going to give you a beautiful answer of 1.215. And that's it, ladies and gentlemen. That is the end of the notes. So no kidding, guys. No kidding, no kidding, no kidding. We finished. We are done with calculus, ladies and gentlemen. We did it. We did the note packet. Woo, 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 woo. I'm so proud of everyone. Fireworks, fireworks. It's so amazing. So, ladies and gents, you're going to try this homework and see how successful you are. Please, 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 please pay special attention to the ones where you're doing the areas. Okay, those are going to be the trickiest ones. And again, in the answer packet, they might have them done different ways, but if you're getting the same answer, then like it's totally fine. Think to yourself, am I actually like putting things together? Is there 2 curves? All this fun stuff, okay? So that is basically it. I am undecided about doing another day on this section or not. I will totally let you know. I'm not 100% sure what's going to be in place for the next day. And then we'll probably like do the group quiz just like as like a assignment for you guys to practice and like so FaceTime with your friends and just try to see that, and maybe that'll be it. Okay. And then we'll put a cap on chapter 11 and that'll be it. So assessing, I don't know. We'll see what comes into play later on. So I think that that's it, guys. I hope you had a fun time. And so I'm going to send you out with some fun music. And I think that's it. So some applause for a wonderful job. Well done. I'm very proud of you. Let me get this guy done. And I'm going to say bye-bye, guys. See you. Bye.